Good afternoon. My name is Jamie Davis. I'm from Virginia Tech, and today I'll be presenting work I did with Eric Williamson and my advisor Dong-Yoon Lee, titled A Sense of Time for JavaScript and Node.js, First-Class Timeouts as a Cure for Event Handler Poisoning. In this work, we made three contributions. First, we define and analyze a denial of service attack against event-driven servers, which we call event handler poisoning. Second, we propose means by which to detect and recover from these attacks. We have both a concept and a working prototype. We call the concept first-class timeouts. Third, we got involved with the Node.js community. We wrote a guide, which you can find on nodejs.org, and we made some documentation changes and implementation changes to core APIs in Node.js to make it a bit safer. In case you don't know, although since this is the web defenses portion, I hope you do know, but Node.js is a JavaScript framework for web services. It's increasingly popular. So it's got about 7 million developers. Its module ecosystem, which is called NPM, has over 760,000 modules. That's a few 100,000 more than the next runner-up. And in July, those modules were downloaded for a combined 24 billion times. Each of those numbers is growing hugely year to year. Node.js is widely used in industry at places including IBM, Netflix, Microsoft, PayPal, Walmart, and it has core support with AWS's Lambda offering. So Node.js is increasingly popular, and it's a thing that we should care about. Let me introduce a little background on web server architectures. You're probably familiar with the one thread per client architecture, or OTPCA. Here we have a dispatcher and a giant thread pool, maybe a couple hundred or a couple thousand threads in it. And when a request comes in from a client, the dispatcher assigns that request to one of the threads. New client, new thread. Because this is multi-threaded, the computation of results will proceed concurrently, and it'll get returned. So in the OTPCA, every client gets its own worker thread. You get scalability via multi-threading. And the classic example of this architecture is, of course, Apache's HTTP server. Let's contrast this with the event-driven architecture, or EDA, as used on the server side. In the event-driven architecture, you have a single-threaded event loop, and you have a worker pool. But unlike the OTPCA worker pool, which had thousands of threads, the EDA worker pool typically has K for a small value of K. The default in Node.js is 4. Node.js has a hard-coded limit of 128. So this is a pretty small worker pool. And each of these event handlers, the event loop and the workers we call event handlers, accept new stuff to do from queues. So if a request comes in, it ends up on a queue. It goes to the event loop to be handled, and the application developer defines what are called callbacks to execute, code to execute in response to these events. In this callback, it looks like the developer offloaded something to the worker pool, so perhaps this is reading a file, and that goes off to one of the threads in the worker pool, the workers. In the meantime, a new request comes in, goes on the event queue. The event loop isn't doing anything right now, so another callback gets executed. Maybe this one's cheap, so we get a response right away. Eventually, the worker pool finishes, so it puts a done event in the done queue. The event loop picks that up and executes the final callback for this request, so we finally get a response. So in the event-driven architecture, we are multiplexing many clients onto a small number of threads, typically for performance reasons. Once you do this, you pay less per client overhead in terms of scheduling costs and memory costs. In the EDA, you have to implement cooperative multitasking. Because you have a single-threaded event loop, no client should be taking too long at any given time. So developers have to partition the generation of responses, and they have to offload work to the worker pool. As I mentioned before, Node.js is the most prevalent example of this architecture today. The server architecture dictates the programming style that developers have to follow. In the OTPCA, you rely on the preemptive multitasking by the operating system, and you write synchronous code that looks pretty normal. In the EDA, you have to implement cooperative multitasking yourself because you have a small number of threads, and the EDA is basically putting the burden on you, the developer, to make sure that all the clients get a fair turn. So in the EDA, you have to write asynchronous code instead. So if I'm writing a file server in the one thread per client architecture, it looks pretty normal. I read the file, I compress its contents, I maybe encrypt the result and return it. In the EDA, I have to write the asynchronous version of this. That's gotten a lot easier in recent years. So async and await are now core asynchronous primitives. So you can say await read file, and this will return a promise and yield control of the event loop to some other client. Once the read file completes off of the worker pool, you can then zip, you await that, you await an encryption, and finally you can return everything. And at each of these await points, the developer is saying yield to some other pending client. So this brings us to event handler poisoning attacks, which occur because the event-driven architecture gets efficiency at the cost of isolating clients onto different execution contexts. In the OTPCA, we dedicate threads to every client. We have thousands of threads, and the OS's preemptive multitasking takes care of us. In the EDA, all the clients are sharing tens of threads, not thousands, and you have to implement cooperative multitasking. The event handlers, the event loop, and the workers in the worker pool are thus a pretty limited resource in EDA-based web servers, and if you can exhaust that resource, you'll get a denial of service attack. So let me show you what an event handler poisoning attack on the event loop would look like. Say I am a malicious client, and I have composed a request that will cause one of your callbacks to take a long time. So here comes the request. It hits the event loop, and we hit the vulnerable callback, which takes longer and longer and longer, and it just takes a really long time. If another client comes in, it will cause an event to occur, but the event loop will never pick up on that event because it's busy handling this maliciously long request. As a result, the event loop is poisoned, and the throughput of the server will drop to 0, denial of service. You can conduct a similar attack against the worker pool. It really depends on where you can find the expensive operation being performed. If you're doing it on the worker pool, then you need to submit some proportion of k, however many is enough to cause the amount of disruption you want. So here is a vulnerable event-driven server. It serves files. So first we do input sanitization, and we say, does the name they're requesting look sort of like a Unix path? It's got a leading slash and some other stuff, and then we put a whole plus around that to say, /A/B/B/C. If the sanitization succeeds, then we will read the file and return the result to the user. So I said there were two EHP vulnerabilities here. The first is that this regular expression is super linear. In fact, it's exponential on malicious input. So this will lead to a vulnerability called regular expression denial of service, or REDOS. If you're curious about that, after my talk is another talk by Chris, who will tell you all about how these happen in the wild. The second EHP vulnerability here is that the input sanitization is on the structure of the file being requested, but it's not taking into consideration which file is being requested. So if an attacker can identify a particularly slow file or a particularly large file, then he can cause the worker that gets assigned to this I/O request to take a very long time. An easy example is if you read from dev random, this uses a good random number generator, i.e. it's pulling from your hardware, and so if you cat that file right now, it'll take a really long time. So we implemented the server in Node.js. It looks pretty much like that code, but with some JavaScript in it. And we conducted an REDOS-based EHP attack. The behavior is pretty much like you'd expect. After some initial startup time, the server reaches a steady state around 1 to 2 seconds, at which point we inject malicious input. In the orange line, which is baseline vanilla Node.js, the server's throughput then plummets to 0 because the event loop is poisoned. Happily, in our prototype Node.cure, we deliver a timeout exception shortly after receiving the malicious input, and the server can successfully detect and recover from this attack, and it returns to the steady state throughput. Event handler poisoning attacks actually happen with surprising regularity in the Node.js ecosystem, which I know because we talked to a company called SNCC.io, which maintains a large database of security vulnerabilities in open source module ecosystems, including NPM. So they shared all 1,132 of their vulnerabilities as of a few months ago with us. And we automatically categorized them by whether they could be used to launch an EHP attack. So about 35% of them could be. including 266 that let you read arbitrary files. That's the IO-DOS vector we talked about. 115 of these denial of service attacks are REDOS, so those are pretty prevalent in this ecosystem as well. So if EHP is happening a lot, what should we do about it? I'll give you two things we shouldn't do about it, and then something that we think we actually should do. So here's our first idea. Why don't we restart the server? We'll put a heartbeat on all of our event handlers, and if any of them stops having a heartbeat, we'll decide the server's dead and restart it. There's really two problems here. The first is that when you restart the server, every connected client has its connection severed, thus achieving the denial of service the attacker wanted all along. The second problem is that there's nothing preventing the attacker from setting up a cron job to submit his malicious input every 10 minutes, so your server's just going to keep crashing and keep coming back. This is not a healthy server. Okay, here's a different approach. We can prevent event handler poisoning attacks if we can partition all of our callbacks and all of our tasks so that they're guaranteed to take no more than some acceptable amount of time. Maybe we can put a constant upper bound on them. So instead of having this sum routine, which goes through the whole list and is O of n, on short lists it'll be fast, and on perhaps maliciously long lists it'll take a long time to compute this sum. We could write this asynchronous routine, which will add 10 numbers at a time and yield, cooperatively sharing the processor time. And once it finally finishes, it'll return the result to the client. On a short list, this will behave about the same, but on a long list, we'll do a little bit of work and then yield, and then we'll do a little bit more work and then yield. And if we add up all of the little pieces of work we did, we'll end up taking about the same amount of time as we did in the original solution, but this way we were cooperative. So this is great. Unfortunately, partitioning is both partial and ad hoc. So by partial, I mean that it can only protect code that's under the application developer's control. In other words, that the application developer is willing to rewrite. That doesn't include all these third-party modules in NPM, which, as I said, has over 700,000 modules and is one of the main selling points of using Node. So that's not great. It also won't protect you against vulnerable APIs in the Node.js framework. That's too bad because all of those IO-DOS attacks are due to vulnerable implementations of IO in Node. And it won't help you from problems in the JavaScript language you're using, which is too bad because all of those REDOS vulnerabilities are due to design decisions by the JavaScript engine implementer. The second aspect of partiality is that partitioning is good for algorithms, but it's really not clear how to meaningfully partition I/O. Sure, you can reduce the block size, but eventually you have to ask the operating system to do an I/O task, and the OS will take however long it wants to. That's not really under your control. And in terms of being ad hoc, partitioning incurs a significant ongoing maintenance burden, because every time you change your code, you have to go back and make sure that it's meeting whatever timing guarantees you used to. So we propose instead first-class timeouts. By analogy first, we have buffer overflow attacks, and for that, modern languages implement out-of-bounds exceptions. Cool. In the server-side EDA, I would argue that what we have here are time overflow attacks, so we can deal with them with a timeout exception. Our idea is to keep the cooperative multitasking guarantees of Node.js, which is sort of necessary for backwards compatibility, but to add in a time-aware component to it. If we can bound the synchronous time of every callback and every task and deliver a timeout exception if those bounds are exceeded, then we can soundly defeat EHP attacks. The refactoring is not going to be too bad. It's an exception, so put a try at the beginning of your function, put an except at the bottom, and you're good to go. And it will be non-destructive. By first class, we mean that the timeouts are being delivered to the application to make a decision about it, and as a result, the application can blacklist or discard the request or whatever it wants to do, and existing clients won't be unharmed. So we've implemented a prototype. This is our desired behavior. It used to be that the event loop would just run forever on malicious input. Now we want it to throw timeout exceptions. Similarly, the worker pool, the workers would run forever. We want them to return timeout exceptions to the event loop for handling. So how do we do this? A Node.js is a JavaScript application. It's strapped onto a V8 JavaScript engine. There are Node.js libraries written in JavaScript and C++. And the C++ libraries go talk to a separate library called libuv, which offers us the event loop and the worker pool. So we made first the JavaScript engine time aware. So we modified V8 so that it knows about timeout exceptions and its exception hierarchy, and so that it has an interrupt handler to cause these exceptions to be delivered. We also made the event loop time aware. So every time you enter a user callback, sort of like leaving the kernel and going into user land, we tell the timeout watchdog, hey, we're going off into user land. Let me know if I take too long. And if the watchdog sees that it takes too long, it goes and tells the JavaScript engine to deliver a timeout exception that will be delivered to the event loop. We also have to protect the worker pool, so we made that time aware as well. We added manager threads that will watch for the workers taking too long, and if they see that, they will dispose of the worker, create a new worker thread, and go back to what they were doing. So our prototype is built on Node version 8. It took us about 4,000 lines of code. We had to touch 50 files all over the place. It is compatible with an asterisk. It's pretty darn compatible. It passes the Node.js core test suite. And we've open sourced it, so you can find it on GitHub there. Our prototype has some security guarantees. So every vulnerable language and framework API is now safe. And because timeouts are composable, applications built with these APIs will also be safe. Cool. Our prototype also passes our EHP test suite, so we invoke all of the vulnerable Node.js APIs with malicious input, and indeed they now throw or return timeout exceptions as appropriate. That test suite covers all classes of vulnerabilities found in the NPM database we mentioned earlier. However, every rose has its thorns. To use first-class timeouts appropriately, it's a detect and response technique. So you have to decide what your timeout threshold is going to be. That's a bit of a Goldilocks problem. It can't be too short, and it probably shouldn't be too long either. And you also then need to decide on a response policy. Maybe you can come up with a very tight threshold, in which case attackers are taking about the same amount of time as normal clients. You don't have to respond much in that case. But if you have a relatively generous bound, you probably want to also implement some kind of blacklisting. We measured the performance costs of our prototype, and we estimate them to be somewhere between 0% and 2.4x in micro benchmarks. And then we downloaded a bunch of applications from GitHub and found that the overheads range between 0% and 24%, depending on the class of application. So not too bad as overhead goes. I promised we also got involved with the community a bit. So we wrote this guide, which you can find on nodejs.org. It's called Don't Block the Event Loop or the Worker Pool, in which we review the Node.js architecture, go through event handler poisoning attacks and examples, and give some advice about using NPM modules safely. So here's a screenshot of the beginning of the guide. It goes on for another 10,000 words or so. I was pretty generous. We also made some changes to Node.js core. We modified documentation for particularly vulnerable APIs, including read file, random bytes, random fill, and spawn. And we put up sort of a test balloon for fs.read file. We modified the implementation so that instead of reading the entire file in a single read system call, it now reads it in chunks, which removes the vulnerability to large files if the attacker can find one. It still doesn't protect the attacker from a particularly slow file, but such is life. In closing, let me summarize. The event-driven architecture has an EHP problem, and we believe first-class timeouts can cure it. In our work, we defined an attack, demonstrated the presence of this attack in the wild. We designed and prototyped a defense, and we disseminated a lot of results to the practitioner community. With that, thank you for your attention. I'd be happy to answer any questions.
We've got time for a few questions.
Hey, I'm wondering if you've observed any issues with asynchronous timeouts resulting in various types of global state, like shared caches and that sort of thing getting corrupted?
That's a great question, to which my answer is we haven't gone and looked a ton at implementation details of a lot of applications. The applications I've looked at sort of manually, a lot of that global state is stored in external places like databases, so the corruption's already taken care of in that regard. If you are doing a bunch of in-heap state management, you would have to handle that in your exceptions.
Thank you.
So what I'm wondering is it possible now some requests are just taking more time than other requests, and how to differentiate that as attack? or a legit request?
So if your application permits some requests to take on the order of minutes, you've simply written your application wrong and there's a terrible performance problem. You should fix that. If your application permits it sort of by accident, it would be difficult to differentiate between a malicious request and one of these sort of valid but bizarre requests. And in this case, even these valid requests would be causing denial of service attacks. So I think ideally, if you're writing an application in the context of first-class timeouts, you would want to reduce the amount of variance that the different requests can have, at least within a given callback or a given task.
So one more question. So what was your experience working with the practitioner community? Were they receptive to this? Did you get any particular pushback in any
Well,
ways?
I'm now a member of the core Node.js development team. And they bought me a plane ticket to Vancouver in October, so they were pretty good.
That's a collaboration we like to see then. Perfect. All right, let's thank our speaker again.